The title of our presentation is Techno-Economic Analysis of Oscillating Surge Wave Energy Converters. My name is Cole Dickerson, and I'm a first-year PhD student in the Department of Electrical Engineering at North Carolina State University. I graduated from East Carolina University last year, where I had the pleasure of working with my co-authors, Dr. Nehat Al-Sawaf from ECU's Department of Economics, and Dr. Tariq Abdel-Salam, who is a professor, the Associate Dean for Research and Graduate Studies in Engineering, and the Director at the Center for Sustainable Energy and Environmental Engineering. To give you context on why this research is important, I'll share a few statistics with you. According to the U.S. Energy Information Administration, the theoretical annual energy potential of waves off the coast of the United States is estimated with a maximum value of 2.64 trillion kilowatt hours. 2.64 trillion kilowatt hours was 64% of the total U.S. utility scale electricity generation in 2021. The Biden administration plans to eliminate fossil fuels as a form of energy generation by 2035. The White House set out a target of 80% renewable energy generation by 2030 and 100% carbon-free electricity 5 years later. With these facts and statistics in mind, you can see that the research and development of wave energy technology for blue economy applications has the potential to expand access to power for remote, coastal, and island communities, improve capabilities to study the ocean, and help to build a diverse portfolio of renewable energy sources that we can integrate into our national power grid. With the motivation for our research established, our primary objective was to perform a techno-economic analysis on two oscillating surge wave energy converter devices and to evaluate the levelized cost of energy, or ELCO, for each device. Techno-economic analysis is a method of analyzing the economic performance of an industrial process, product, or service. It typically uses software modeling to estimate capital cost, operating cost, and revenue based on technical and financial input parameters. ELCO measures the lifetime cost of a device divided by energy production and is the metric we chose for our techno-economic analysis. For context, the ELCO of solar energy is 6 to 8 cents per kilowatt hour, and wind is 2 cents per kilowatt hour. An oscillating surge wave energy converter, or OSWEC, is a device that harnesses the power of ocean waves by using a floating structure that moves with the waves. As waves pass, the device oscillates, driving mechanical components like pistons or turbines to generate electricity, converting wave motion into usable energy. The figure on the left details this process. The picture on the right shows a 1/10 scale model of one of the OSWECs simulated in the study. It was taken to East Carolina University's Coastal Studies Institute for testing in a wave tank housed there. A critical part of harvesting electrical energy from the ocean is identifying potential WEC deployment sites and characterizing the wave resources there. Sandia National Laboratory, or SNL, published a report that presented important wave statistics at a variety of testing locations, allowing researchers to choose the site best suited to their device and testing needs. ECU's Coastal Studies Institute partnered with Jeannette's Pier in 2004 to encourage research and innovation around wave energy devices and other ocean technologies. The Jeannette's Pier Wave Energy Test Center has two mooring locations at 6 and 11 meter depths respectively, each within 600 meters of the pier itself. Jeannette's Pier is listed by the report as being well suited for smaller scaled devices like the two OSWECs featured in this paper. A 31-year hindcast dataset was created by CSI researchers for the offshore regions of North Carolina's coasts. The wave resource characterization at Jeannette's Pier uses this dataset to calculate statistics of interest. Historical data from wave rider buoys were used to calculate representative spectra and extreme wave conditions. The report includes joint probability distributions of the significant wave height and energy period, which are shown in the next two slides. This slide shows the frequency of occurrence of each bend C state at Jeanette's pier site. The majority of waves have an energy period lasting from 4 to 9 seconds and a significant wave height of between 0 and 2 meters. The report also shares the percent contribution to the total wave energy of each bend C state. Again, as you might expect, the waves that contribute most to the total energy are the ones that occur with the most frequency. Therefore, the waves that contribute most have an energy period lasting from 4 to 9 seconds and have a significant wave height of 0 to 2 meters. This data is crucial to the calculation of electrical power matrices and to the evaluation of ELCO for each device. The following slide shows the geometries of the two Oswec flaps studied in our paper. The flap on the left was shown in the picture in an earlier slide. Each device was designed in SOLIDWORKS to obtain the mass properties for each device and to generate .step files which could be imported into the mesh generating software Rhino. The physical dimensions of the Oswec were chosen specifically to optimize the energy harvested from the wave resources at the Jeanette's Pier Wave Energy Testing Center. The generation of mass properties was a very crucial aspect of this study, as the mass properties were input variables into the simulations used to calculate hydrodynamic coefficients and power performances for each Oswec. Both Oswecs had a chosen density of 250 kilograms per meter cubed, which was a little less than a quarter of the density of seawater. Both Oswecs were 13.2 meters wide, 13.2 meters tall, and had a maximum thickness of 1.8 meters. Our simulation workflow was as follows. WAMET is the BEM code we used in our simulations. It is a software used to analyze the interaction of surface waves with floating and submerged structures. It calculated hydrodynamic coefficients using two subprograms, POTEN and FORCE. POTEN computed radiation velocity potentials and diffraction components, while FORCE calculated global quantities like hydrodynamic coefficients and forces. These calculations generated formatted output files containing hydrostatic and hydrodynamic data. Then, Beamio, a MATLAB script, pre-processed the hydrodynamic data from WAMET for use in WEXIM, an open-source simulation software for wave energy converters developed by the National Renewable Energy Lab. WEXIM simulates WEC dynamics, including multiple bodies, power takeoff systems, and mooring configurations to assess electrical power output and dynamic responsiveness to ocean waves. The methodology for running WEXIM cases was adopted from NREL's Reference Model 5 report, ensuring accuracy with a ramp time of 100 seconds, a duration of 400 seconds, and a 10 millisecond time step. Irregular waves were modeled using the Pearson-Moskowitz spectrum, with consistent random wave phases for each simulation. Various parameters, including PTO stiffness and damping, were optimized for each wave condition. Multiple WEXIM cases were run to find the optimal combination of stiffness and damping for maximum power performance in different sea states. A user-defined function processed mechanical power output into electrical power, considering a conversion efficiency of 82.5% based on the literature. These values were organized into electrical power matrices found on the next slide for analysis. The annual energy production, or AEP, was calculated using the wave statistics from Jeanette's Pier, electrical power matrices for the Oswecs, which are shown on this slide, and the conversion losses from the hydraulic PCC system. Power generation performances in irregular wave conditions were represented with power matrices from WEXIM. Electrical power matrices were estimated by multiplying mechanical power matrices with PCC conversion efficiency and limiting maximum power output at the rated power for each device. AEP was calculated by summing the products of electrical power matrices and wave statistics. The rated power was based on a 30% capacity factor. Device 1 had a rated power of 150 kilowatts and an annual energy production of 367.25 megawatt hours. Device 2 had a rated power of 62.27 kilowatts and an annual energy production of 152.46 megawatt hours. The factors for calculating the levelized cost of energy for ocean wave energy converters include the device's lifetime, discount rate, CapEx, installation and manufacturing costs, and OpEx, ongoing maintenance costs. Assumptions from previous studies were used to derive baseline CapEx and OpEx values, which were then scaled by mass. Mass scaling is justified by the direct relationship between device mass and material cost, including mooring components. Heavier devices require larger moorings and materials, leading to higher CapEx and OpEx costs. For example, Flap 1 had a mass-scaled CapEx and OpEx values of $9,080 per kilowatt and $484 per kilowatt, while Flap 2 had values of $9,058 per kilowatt and $483 per kilowatt, respectively. Baseline ELCOs for both OSWEC flaps were calculated over a 20-year lifetime with discount rates of 3, 7, and 10%. The choice of a 20-year lifetime aligns with NREL's typical calculations, while the selected discount rates follow International Energy Agency standards. Lower discount rates result in smaller ELCO values. The primary objectives of this study were to perform a techno-economic analysis on 2 OSWEC devices and to evaluate the ELCO for each device. Our contribution is twofold. First, we generated original datasets for mechanical and electrical power matrices of 2 OSWEC geometries. Second, we calculated the ELCO values at varying discount rates for both OSWEC geometries. The calculated ELCOs for the first device were $3.55 per kilowatt, $6.10 per kilowatt hour, and $9.64 per kilowatt hour for discount rates of 3, 7, and 10%, respectively. The calculated ELCOs for the second device were $8.53 per kilowatt hour, $14.67 per kilowatt hour, and $23.16 per kilowatt hour for discount rates of 3, 7, and 10%, respectively. These findings are in line with earlier research and showed that the ELCOs of pilot scale projects did not cost competitively compare to those of other renewable energy sectors. The goal levelized cost of energy for early market commercial scale wave energy products should be less than 30 cents per kilowatt hour, following the example of the more developed offshore wind energy sector. More research is needed in the following areas to reduce the levelized cost of energy for wave energy conversion products. Higher fidelity evaluation and reduction of CapEx and OpEx, possibly through alternative materials like inflatables. Original power matrices of various OSWEC geometries collected from real devices in the WEC industry. Continued development of programs for numerically simulating WEC and WEC arrays. Monitoring of wave conditions to optimize electrical power generation, and the development of control systems to optimize energy output. We want to thank you very much for attending our presentation. Unfortunately, I had a wireless networking exam during my presentation slot and was not able to present live. So if you have any questions, please feel free to reach out and email. Thank you again.